Projector's warming up. Let's try to remember what we were doing a week ago for the test. I haven't quite finished grading the test. It's looking pretty good. It looks like you're pretty solid on the basics, so that's encouraging and means we can move on and build on that. So I'll finish grading it probably tomorrow. Today's really busy. And I'll post the grades on Canvas, but I obviously won't see you again until Tuesday, so can't actually hand them back until then. So let me remind you that we were talking about solid objects, talking about metals because they're kind of simpler. And we were modeling a solid object at the microscopic level as a network of atoms, a lattice of atoms connected by covalent bonds. And these covalent bonds, it turns out, are very spring-like in the sense that if you exert a force, you stretch it a certain amount, and if you exert twice the force, you stretch it twice as much. And so the enterprise that we were engaged in and didn't quite finish last Thursday was to determine the spring stiffness of one of these interatomic bonds modeled as a spring. And we'd gotten to the point where we had actually calculated the length of one of these bonds, the distance between the center of one atom and the center of the next atom being the spring, and that was the same as the diameter of an atom, it turned out. And we found that for copper, based on the density of copper and the molecular weight of copper, we actually calculated that distance as being 2.28 times 10 to the minus 10 meters in a block of copper. And for other substances like aluminum or lead, the atoms have more electrons or fewer electrons, so they're going to be a little bigger or a little smaller, but there should be on the order of 10 to the minus 10th meters. That's about the size of an atom. And then we started on a quest to try to figure out the stiffness of one of these springs, and to do that we had to think of a wire as a network of balls and springs, and we took a side trip because we had to figure out how springs hook together in parallel compared to single springs, and how springs chain together in series, single springs. And so we worked on that for a while, and we got to the point of saying that if we had n springs in series, which means end to end, that the stiffness of this whole series of springs, I sometimes write the effective spring stiffness of the whole thing, K effective, but what we mean is the stiffness of this whole series of springs proportional to the stiffness of one spring. How? So it was 1 over n, wasn't it? Because it stretched more when you hung the same weight on it. And if we had n springs in parallel, meaning all contributing to supporting the same weight, that was equal to, that was proportional to the stiffness of one spring. How? It was n times much stiffer, so it was. And so now we're in a position to use some real data and actually figure out the stiffness of one of these interatomic bonds in copper. And the way we do it is by taking a copper wire of some length and just hanging weights on the end and seeing how much the wire stretches. And that's something you'll actually do in lab next week, I think. And so if we consider a copper wire that's 2 meters long, and just to make our calculations easy, we'll take a wire of square cross sections. So it's if you look at the wire stretched out this way, it kind of looks like that. So and this area is called the cross-sectional area of something. And so each of these sides is 1 millimeter. And we need to know these dimensions because we need to be able to count the number of chains of atomic springs we've got in this wire. Now we could have done round, but this just makes it easy. And we find that if we, so here's our wire, and if we hang a 10 kilogram weight on it, it stretches 1.67 millimeters. So not a lot, but enough to measure. So what we want to be able to do is use these relationships to figure out the stiffness of one of these little interatomic springs. And to do that, we've got to figure out in this wire of square cross section how many springs we have in parallel, and then along the length of it how many springs we've got in series. And then we can use that with the spring stiffness of the wire as a whole modeled as a spring to get the stiffness of one of those little interatomic springs. So first of all, let's find out the stiffness of this whole wire. So we'll call this the spring stiffness of the entire wire. So if we think of the entire wire as one long series and parallel spring, one long spring, how do we get the spring stiffness of the wire?
Find out how many springs there are.
What?
We need to find out how many springs there are.
No, we have to find out how many springs there are, but suppose we just say this wire, we're going to think of this wire spring. Okay? So we're pretending it's one big spring. What's its spring stiffness? How do we get that?
Is it the sum of the series and the parallel?
It is, but let's just get it from, so we're just being macroscopic for a minute. We're not drilling down. We're just going to say, so just as we had a chain and we measure the spring stiffness of the chain, then we could get that. Yeah, Altera?
Well, the force of gravity is equal to the force of the spring.
There we go, back to the momentum principle, right? Yeah. So we're going to say that the momentum of this block is not changing. So delta P is F net delta T for any given delta T that we're interested in, and we're about to make this an instantaneous thing by taking derivatives a little later. But for now, take a second. Then we say if the momentum change is 0, then the net force has to be 0. And so we know there's a gravitational force down on this block. We've chosen the block as the system. There's a spring force up, which is due to the wire thought of as a spring. These two have to be equal. So we can just work with y components here, right? So we say the change of momentum in the y direction over some time is the y component of the gravitational force plus the y component of the spring force, and therefore we know that this is going to be equal to a minus m times g, and this force is in the plus y direction, so it comes out to k sub s times s, and so k sub s is just going to be equal to mg divided by the stretch, so that's 10 kilograms and 9.8 newtons, per kilogram, divided by, what's the stretch? 1.67 millimeters. And so, if we work that out, we get the spring stiffness of the wire as a whole is going to be pretty high. It's 5.87 times 10 to the 4th newtons per meter. Now we can do what you wanted to do a minute ago and use those relationships, right? So first we need the number of parallel chains. So how are we going to get that? So the length of the wire doesn't give us the number of chains in parallel. What we have to do is look up from the bottom and basically count the number of atoms we see from the bottom, right? Because each atom is the end of a parallel chain. So what we need to do is stand under the wire, look up, and just count the atoms in the cross-section of the wire. Okay, well, we can't do that, but we do know the cross-sectional area of the wire. So the cross-sectional area of the wire, if we have that, so here we're looking at the cross-sectional area of the wire, and here are all the atoms. So if we say, well, we know the cross-section of the wire. We basically know the area occupied by one atom. If we draw a little square around this atom, that's the area, the piece of the wire that's occupied by that chain. So we could actually say that it's the cross-sectional area of the wire divided by the cross-sectional area of one atom, and that would give us the number of atoms here, right? Number of chains. And so that's just, we said it was 1 millimeter by 1 millimeter, right? So 1 times 10 to the minus 3 meters squared divided by, what are we going to use for this area of an atom? So we're talking about squares, we're just going to square that, right? So 2.28 times 10 to the minus 10 meters squared. And that gives us, I checked this morning. So this is actually kind of an interesting number. So this is actually, this comes out to 1 times, this comes out to 5.2 something, 5.2 times 10 to the minus 20th meters squared. And so it's going to be a big number, right? About 1.92 times 10 to the 13th. Because atoms are really small. Okay, questions about that? Yes?
Where did you get the 1 times 10 to the negative third number?
That was the length of one side of our wire here. So our wire had a square cross section. It was a millimeter this way and a millimeter that way. And so to get that cross sectional area, we just multiply a millimeter by a millimeter. Okay, other questions? Okay. And now we have to calculate the number of so this, we'll call this in parallel. The number of springs there are in one chain, right? So we need the number of series. And how are we going to get that? So we know the length of the wire. Yeah, so we know it's just the length of the wire divided by the length of one bond. So that's 2 meters divided by 2.28 times 10 to the minus 10 meters, which is what we got for the length of one bond, which I just erased, I think, right? That was right, wasn't it?
Yeah, it's on the board.
Okay. And so this is going to come out to something like 8 times 10 to the minus 9th. That's going to come out to the 9th. Sorry, 8 point 10 to the 9th chains in parallel. So we know the number of parallel chains, and we know the number of springs in each chain. So we know that the spring stiffness of the wire as a whole is related to the spring stiffness of one, I'll call it K sub SI, the interatomic spring. By that relationship we discussed earlier. So what do we do with this number, the number in series? We're going to divide by, right? So we want in series, what are we going to do with the number of parallel springs? Multiply by it. And so solving for K sub S interatomic, we have K sub S of the wire times in series over in parallel, and that's equal to the K sub S of the wire was 5.87 times 10 to the 4 newtons per meter. We had 8.77 times 10 to the 9th springs in series. We had 1.92 times 10 to the 13 springs in parallel. Lots of big numbers here. And when we work it all out, it comes out to something like 26.8 newtons per meter, a really ordinary number, so about 27 newtons per meter. You're going to do some experiments with springs and masses in lab, and the springs you're going to be using have spring stiffnesses kind of like that, 10, 20, 30, 40 newtons per meter, so it's a pretty ordinary spring stiffness. Now it turns out that the spring stiffnesses of, so we actually, from a macroscopic measurement, we hung weights on the end of a wire, and by doing that we figured out the stiffness of one of these interatomic bonds modeled as a spring. So we went from a macroscopic measurement to learning something about what's going on inside this material. Now what can we do with a number like this? Well, we can predict something kind of interesting. So here, so we can predict what's called the speed of sound in a solid. What does that mean? Well, it's really at the speed of a disturbance in a solid. So imagine a long bar of metal, and so we'll pretend this is metal, and suppose I just tap on the end of a bar. Well, think about what this is doing to the atoms in this bar of metal. It makes the atom on the end move in, right? But that compresses an interatomic bond between this atom and the next atom. And so now there's a force on this atom, and it's going to move, but now it's compressing the next spring. So it's something like this is going to happen. If we move that atom, now we're not drawing the springs here, but imagine the springs. We've compressed a spring, and so now there's a force to the right on this second atom. And so in the next time interval, as I keep clicking, these atoms move, but now this atom is compressing that spring, and that atom is compressing that spring. Now notice that these guys at the end, the right end, they have no idea anything's happened yet. So the fact that they don't know, the guys at this end don't know that I've hit this end of the bar, because this disturbance is propagating atom by atom through this bar and just hasn't gotten here yet. But we'll keep going, and eventually we'll get there. So finally something's starting to happen here. Now, a nice way to see this a little more visually is if we graph the displacement of an atom from its equilibrium position. Okay? So right now everybody's sitting at their equilibrium position, nobody's displaced. But then we've decided the displacement to the right is a positive plus x displacement, and that's the only one that's moved. But now this one's a little bit displaced from its equilibrium position, but now this one is to the left of its equilibrium position, so its displacement is negative. And we can see on the graph this disturbance working its way down the chain, hasn't gotten to the last atom quite yet, but now it finally starts to feel it. So that's kind of an easier way to see the disturbance propagate. Okay, so how fast does this propagate? Well, what we've done here is just written a computational model where we make a chain of 100, in this case I think we're working with aluminum, so 100 aluminum atoms connected by springs. And we're just doing an iterative calculation. So a force gets applied to this atom, and in the next time step, the momentum of this atom increases to the right. And now what we've got is this spring compressed. Now there's a force on that atom, and a force on this atom going that way. So it starts moving to the right. Nobody else has moved yet. But now, in the next delta t, this atom's moved to the right and compressed this spring. So now this atom feels a force this way, and that atom feels a force that way, and this atom is probably being pulled back by now because... And so, so iteratively, what this computer program does is just step through it and say, at every time step, I'm going to look at every atom in the chain, and I'm going to see if either of the springs on either side of it is compressed or stretched. And if they are, I'll calculate the force, and if I calculate the change in its momentum. So this is the same thing you do for one atom on a spring, except we're just doing it for all of them, and each of them has two springs. So that's what the program does. And then we're just going to see how long it takes empirically to get there. So here's going to be our graph of displacement versus time. We have 100 aluminum atoms, which is really only 2.58 times 10 to the minus 8th meters. Okay, so that's a really small distance, but if we made it 2 meters long, our program would take a really long time to run. And we're going to do this a little bit roughly. So how we're going to measure it is just set it going, and then when we think it's gotten to the end, I'll click again to stop it, and it'll just measure how long it took in the computer's virtual time to get there. So let's go. Not there, not there, not there. Now, whoa, it didn't, okay, that didn't get that click. Let's try that again. There we go. Let's try again. There we go. So, it divided the distance by the time, and so the speed of sound was 4,971 meters per second, which isn't very accurate because it depended on me clicking, among other things. But actually, this measured value for the speed of sound in aluminum is 4,800 meters per second. So for a simple model, with a very rough termination, that's not bad at all. We predicted, just from knowing the interatomic spring stiffness, which is a little different for aluminum, we predicted the speed of sound in aluminum. And the one way you can measure the speed of sound is by, you take a bar of aluminum and stick a microphone here. And if you tap it with a hammer here and start a computer sensor going, like your computer interface upstairs that's just connected to the microphone, just time it until the microphone hears something, and then, so you can actually measure it that way, and you can get the number that way. There are more accurate methods. So we can do that. Well, okay, so this worked for aluminum. Let's see if it works for a different material. So let's consider lead. Now, think about aluminum and lead. Which one is stiffer? Aluminum. Lead's really very soft. It's not good for you to touch it with your bare hands because it's quite toxic. But if you wear gloves and you touch, you find that you can actually deform a sheet of lead yourself. So it's much softer. So should the speed of sound, should it take longer for the disturbance to propagate, or should it be quicker? So you're saying longer, smaller? Okay, so we still have 100. Okay, so this is a chain of 82 lead atoms. Okay, so let's see what happens. So we'll bang on this end. Whoa. It's really slow. Those soft springs take a long time to exert a force, and so maybe I can do a better job of clicking when we get to the end, which is now. Okay, so we calculated a speed of sound of 1,242 meters per second, and the measured value for the speed of sound in lead is 1,200 meters per second. So again, pretty good for a simple model based on our calculations of interatomic spring stiffnesses. So by hanging weights on the end of the wire, we actually were able to predict the speed of sound in a material. Does anybody happen to know the speed of sound in air? No, it's about 330 meters per second. So the way I remember it is that between when you see the lightning flash and when you hear the thunder, that's about 3 seconds per kilometer. So about 330 meters per second. So much slower than the speed of sound in these metals, which is quite high. So that's a little unexpected and sort of cool. Questions about that? Yes?
So if it's like a softer element, it means the springs are softer?
Mm-hmm. It means the chemical bonds aren't as stiff. Yep. Yeah.
What about liquids?
Liquids are more complicated because in a liquid, and it of course depends on the liquid, the molecules are attracted to each other, but of course they can move all around. They're not in this nice array. So you can still get a pulse going through a liquid, but it's not as if there were covalent bonds between the molecules in the liquids. There may be ionic attractions, like hydrogen bonds in water, for example. But it's going to be a little bit more diffuse. But it's kind of the same mechanism. It's the same mechanism in air, which is a gas. So in air, if I clap my hands, I displace some air molecules. And they move away, and they run into some other air molecules, which move that way and that way and that way, and the sound spreads out throughout the room. So the people in the back row actually heard that clap, but not exactly at the time I clapped. It was, well, 330 meters per second, and we'll call that what? 4 meters? Well, how far? 10 meters? 10 meters? Okay, so it didn't take very long. A few fractions of a second, but you heard it later than the
What about the mass of the lead versus the mass of the aluminum?
Well, what do you think? What about the mass? Do you think that matters? So which has a higher atomic mass, lead or aluminum?
Lead.
Yeah, so it kind of takes a bigger force to get those lead atoms going, doesn't it? So that's gonna make it slower too, isn't it? All right. Now, at some point, one of you asked, what about, so the spring stiffness is just a property of an individual spring, right? Now, this interatomic spring stiffness is a little more a property of a material. But spring stiffness of the ordinary springs is a property of a spring. What if we took a macroscopic view? What could we say that is a property of copper in general, rather than telling people, yeah, we know the stiffness of an interatomic spring in copper is 27 newtons per meter, and so we can use this to calculate how much a copper wire will stretch if we know its dimensions. So we want something, so we're going to talk about some concepts. There we go. Concepts related to macroscopic objects. And the idea is we want a sort of a macroscopic measurement we can make, a macroscopic number that tells us, that lets us compare the deformability of different materials. And that quantity is called Young's modulus. It's not a very romantic name, but it does capture this deformability of a macroscopic thing independent of the geometry of the particular object. So whether our copper wire is 50 centimeters long or 2 meters long, whether its cross-sectional area, whether its diameter is a millimeter or 2 centimeters. And so it's a macroscopic measure of stretchiness. And it's defined as, it has the symbol Y, it's defined as the ratio of what is called stress to what is called strain. So what are stress and strain? Well, strain is basically fractional stretch. So it's defined as if you hang weights on a wire, so the thing we're doing here is hanging weights on a wire. So this is the change in length of the wire over the original length of the wire. So this is basically stretch. And this is the relaxed length of a wire. Okay, so in our example before, we had a copper wire that was 2 meters long, and the stretch, it stretched 1.67 millimeters. So what was the, how would we calculate the strain here? So how do we calculate the strain?
Find the difference.
So it's the stretch over the original length, right? What's the stretch of this wire? Okay, so it's equal to 1.67 times 10 to the minus 3 meters. What was the original length of the wire? 2 meters. And so that's going to come out to be kind of a small number. That comes out to 8.35 times 10 to the minus 4th meters. Now, what would this strain have been if we'd used a 10, so this is 10 kilograms, a 10 kilogram mass, but the wire was only 1 meter long? What?
Meter, it's not meters. The strain wasn't. There were meters over meters, you did.
Oh, unitless. Thank you. So what happens what if we hung the 10 kilogram weight on a wire that was only 1 meter long? How much would it have stretched? Half as much, okay? So suppose we had 1.67 times 10 to the minus 3 meters divided by 2 for the delta L, and this was 1 meter. What's the strain going to come out to be? Exactly the same. So this is independent of the length, because it's a fractional stretch. It's independent of the length of the wire, which means that we're getting rid of one geometric factor. Now the other factor we'd like to get rid of is cross-sectional area, because we want something that's independent of cross-sectional area of the wire. And so let's think about that. So 4.6C. So how is this going to work out? Imagine hanging 10 kilograms from our copper wire and we get an 8 millimeter stretch. And then we take a second copper wire that's the same length, but its cross-sectional area is only half as big. So how much do you think it's going to stretch? So what's going to happen? What's the answer? So what have we done to the number of parallel chains? Yeah. So how far is it going to stretch? It's going to stretch twice as much, isn't it? Because there's only half as many chains supporting so we have half as many parallel chains supporting this weight. So each one has to support twice as much as it did before. So it's going to stretch twice as much. So the stretches. So we need to get rid of this, and so what the stress is defined as is the the force acting on the wire, and we call this a tension force, divided by the cross-sectional area of the wire. So we have a force per area. So in our example here, using the wire we used originally that had a 1 millimeter by 1 millimeter cross section, so we have this 10 kilogram mass. Wire was we had so this is we called it a spring force exerted by the wire. This is usually called a tension force. And in fact, a tension force, so why is it called a tension? We often say, what is the tension in the wire? Now that's kind of an odd way to say it, because we know that the wire is exerting an upward force on this block. What does it mean for tension in the wire? And the thing to think about is to think about like some location in the middle of the wire. So we'll blow it up here. So here's our wire, and we see that this part of the wire has to exert an upward force on that part of the wire, right? So every part of the wire has to be exerting, so this, every atom in here has to be exerting upward forces, and they all have to add up to this force plus the mass of the wire below it, the force on the gravitational force on the mass of the wire below, which isn't very big. We usually ignore that. So it makes sense to call this the tension in the wire. Okay, so for our copper wire, what was that force? How much weight were we supporting here? 10 kilograms, right? So this force we decided was equal to 10 kilograms times 9.8 newtons per kilogram, so 980 newtons. And what's the cross-sectional area of the wire? Well, it was a millimeter by a millimeter, so 1 times 10 to the minus 6 square meters. And that comes out to something a little bit less than 9.8. It's 8.35 times 10 to the minus 10 to the plus, isn't it? Let's calculate it. There we go. Oh, we're already logged into GlowScript. We are. So how are we going to calculate this? Call it stress. So it's 10 kilograms times 9.8 newtons per kilogram divided by 1 times 10 to the minus 6th meters squared. What are the units going to be? So we got this meters squared in the denominator. We've got newtons in the numerator. Looks like it's going to be newtons per square meter, right? And so to get Young's modulus, we're just going to divide stress by strain. So that's going to be equal to 9.8 times 10 to the 7th newtons per square meter divided by 8.35 times 10 to the minus 4th with no units. And let's calculate that. No. What did I do? Okay, we've got to make this smaller so I can see what I'm doing. Oh. It helps to have an equal sign in your calculation. Okay. So it's something on the order of 1.2 times 10 to the 11th. And the units would be newtons per meter squared. So it's basically a unit of pressure, often measured in kilopascals. Now when you try to measure Young's modulus, so if you plot stress over strain, or actually when you plot, what you're really measuring is your hanging weights. So you should get a straight line because it's a proper. And that's actually true until you hang too much weight on the wire. And then what actually happens is you actually start changing the internal structure of this material. Some of these chains slip past each other and you get something that goes like that. And so then you hopefully you stop before that. It's actually yielding. Now, there's a simple way that we can relate our microscopic to our macroscopic view here by considering the following thing. Suppose we just consider our two atoms and one bond. and we say, how would we calculate Young's modulus for this one atomic bond long wire? So Young's modulus would be stress over strain. Well, what's the stress? That's just going to be the stretch divided by the length of our interatomic bond, right? So just the stretch divided by D. And that's the strain, sorry. That's the strain, that's the fractional stretch. What's the stress? Well, it's this force exerted by the spring over the cross-sectional area. So it's sort of, that's going to be the interatomic spring stiffness times the stretch over the cross-sectional area, which is going to be d squared. And some things cancel here. The stretch cancels out. One of the d's cancel, and we actually find that Young's modulus should be equal to our interatomic spring stiffness divided by the diameter of one atom, or the length of an interatomic bond. Okay, questions? So we talked about tension forces, stretching wires, but what about compression forces? So clearly the same process is happening in reverse. We're compressing these interatomic bonds in the table. And so we have a picture, actually something a little bit like this, of what happens when we put, say, a brick on a table. So it's the same kind of deal. We've got the table, the compressed springs, these compressed bonds in the table or the block of metal or whatever the thing is sitting in, exert an upward force. The earth pulls down. If the momentum of my teacup isn't changing, that must mean that these two forces are equal in magnitude, opposite in direction. This force by the table is often called, you may have seen this in a previous physics course, this kind of compression force is often called a normal force. What on earth does that mean? What's normal about it? Or does it mean like normal school where we train teachers? No. What it means is it's perpendicular to the surface, that's all. So it's not, it just means it's the mathematical normal. So you may see it written as Fn, a normal force, but that's all we're talking about. And again, Young's modulus will tell you how much the table will compress or not compress. What happens if we pull the brick to the right? So we apply a force to it, and we pull it. Well, this teacup, or our brick, has actually sunk down into the table a little bit, right? And so as we pull it, it's actually running into some atoms and bonds there. And what are they going to do? So here's our brick sunk into the table. As we pull it this way, the table's going to exert a force back, isn't it? So what's that force called? Friction. That's friction. That's friction. Now, so really the table is exerting one force on this brick. It's got an upward component to support it and a backward component because but it's pretty common to analyze these situations by dividing this force by the table into two components. So we say that it's the sum of often we use a lowercase f for friction force, and this perpendicular component, the normal force. And we can do that. It's just a mathematical move, really. We're just saying we can always express a vector as the sum of two other vectors. And it's convenient to do it this way because then we have one force that's perpendicular to the table and one force that's parallel. So it's a convenient move in analyzing it. Now, if we made our brick twice as heavy, it's going to sink into the table even more, right? So what do you think that's going to do to the friction? It'll increase it, right? So the amount of friction really depends on the mass of the object. And so empirically, we write friction force. So it depends on the mass of the object, but it really depends on, why does it depend on the mass of the object? It depends on how much those springs are compressed. So it depends on how big the force pulling the brick down into the table is, which is the same magnitude as the force pushing up by the table. So we often say friction is proportional to this normal component of the force by the table. And that proportionality constant is called the coefficient of friction. And this is the Greek lowercase mu. And this is a very empirical number. People just measure it. Now, it really is related to Young's modulus in the sense that the softer the table, the farther down the block is going to sink, and so the bigger the friction is going to be. But it's also related to how rough the surface of the table is and how rough the surface of the brick is, which really varies from object to object. And so these coefficients of friction are very empirical things. And in fact, it turns out there's not one but two coefficients of friction. So if the block is sliding, then we call this the coefficient of kinetic friction. That's just a fancy way of saying moving. It comes from the Greek. So now, and so that's actually, here's going to be our friction force. Here's the force, the upward component of the force by the table, and so this is going to be equal to this coefficient of kinetic friction times this normal force. And that's pretty easy to calculate. But there's another situation where, suppose we're pulling this block, but it's not moving yet. We're just not pulling it hard enough to move it. So it's at rest. Now it's at rest because of the friction force. So we pull with some force pulling. We have this friction force going backwards. The block's not moving yet. So we're going to pull a little harder, okay? So we pull a little harder. The block still doesn't move, but what has to be true about this friction force? It got bigger too, didn't it? So up to some point when we finally exert enough force to move the block, and then it starts to slide. So this situation is called a static, no motion situation. And the friction force in this case, it can increase up to some value. And then finally, when it gets to that value and you exert a bigger force than that, it breaks free and slides. So we actually write it as the friction force is less than or equal to a different coefficient of friction called coefficient of static friction times the normal force. So there are these two regimes. So let's see. Okay, so we have a 100 kilogram block here. It's on the floor, and we're not pushing, we're pulling. Okay, I mean we're not pulling, we're pushing here, but we're exerting a force of 400 newtons. The coefficient of static friction is 0.6. So what's the magnitude of the frictional force on the block by the floor? This is slightly a trick question, so think about it carefully. Try the momentum principle. Okay, what's your answer? Okay, if you don't know, then talk to your neighbor. Okay, let's draw a force diagram for our block here. So here's our block. We're pushing it. There's a friction force. There's also the gravitational force and this normal component of the force by the table. So what do we know about these two forces? They're equal and opposite, aren't they? Because the y component of momentum of the block isn't changing. Is the x component of the momentum of the block changing? Not moving, right? What do we know about these two forces? They're equal. How big is the friction force? 400 newtons. Okay? So that was, you didn't need this coefficient of friction, but how big a force would you have to exert to get it moving? How big a force do we have to exert to get it moving? So what's the biggest friction force that the, what is it, a table? Floor. What's the biggest friction force the floor can exert before the block starts to move? How do I calculate that? So how do I calculate it? 0.6 time divided?
I don't know what I was doing. I saw that, I'm like, oh, that's division, but it's not.
No, it's not division, is it? So, and what's this force? This is Rebecca.
Opposite gravity.
So this is the magnitude of this is 980 newtons, right? And what's 0.6 times 980? Okay, so you have to exert a force of at least 588 newtons to get it moving. Questions? Yes?
Is it 588 newtons to get it moving, or is it to be equal to the friction?
So 588.1?
So something arbitrarily small.
Yeah, I mean, so it's, this force can get up to 588 newtons, so if you exert just a teeny bit more than 588 newtons, the block will start to move, right? Okay. One more. Okay, a different floor. We got it moving, actually, we finally got it moving, okay? So the coefficient of kinetic friction and the coefficient of static friction can be different. So it's finally moving. So now the coefficient of kinetic friction is 0.3. And we're pushing this block, we're pushing with a force of 400 newtons. What happens to the speed of the block? So how do we decide if it's speeding up, slowing down, or moving at constant speed? We have to find the net force acting on the block, don't we? So how do we find the net force acting on the block? So here's our block. We're exerting a force of newtons. How big is the friction force? 294. It's 294. How did you get that? So that's 0.3, the coefficient of kinetic friction, times the normal force, so 980 newtons. Okay, so the net force is to the right. So what's happening to the block? Speeding up. Speeding up. So it takes a minute to process this case where you can exert a force up to this without moving the block. Then once you get it moving, the coefficient of sliding of kinetic friction might be smaller. Okay? Good. We'll work on this in recitation.